Thank you, everyone, for being here. To begin, something we hear quite often, we've been talking about MLOps for the past several years at GTC, is that MLOps is confusing. And that might be because a lot of people's first introduction to MLOps are these sort of like architecture slides, where you see all these different components and how they interact with each other, and it gives you this sense that you kind of need to build your MLOps or AI platform using the exact same components. But the problem with this, of course, is that some of these representations are built by just particular organizations or companies that they might be trying to sell you, exactly the components that they might have. Another kind of issue with this is, another issue is like architecture slides that are just extremely detailed, right? That show you every step in the process, and maybe they're focused on just one particular type of ML problem. Can get very detailed, can feel overwhelming. And what's even more overwhelming is when you look at the landscape of every sort of solution that declares that they are part of the MLOps ecosystem, and some of them are overlapping with each other. Some of them do more than others do. Some of them are only kind of tangentially supporting MLOps, right? So it's easy to get overwhelmed in this space. And it can often feel like this sort of allegory of, blind monks examining an elephant and trying to describe what an elephant is, right? So we'll try to avoid that in this talk. And I hope by the end of the talk, you'll get a good sense of what MLOps really is and what it's about. So we'll start with what the process is to building ML. And one thing to keep in mind as we talk through MLOps is that it's a combination of science and engineering, right? The scientific method needs to be applied. We need to kind of check our assumptions. We want to follow a rigorous process to arrive at what the truth is for the particular problem that we're solving. And then from the engineering perspective, it's not enough to arrive at the truth, because we have to deploy something that operates in the real world. And there might be sort of assumptions that get challenged once we actually deploy in this real world. So we have to also engineer a solution in an effective way so that it meets those challenges. By the end of this talk, we'll go through the kind of components that you should consider if you're building an ML platform, and they'll be broken down into this kind of scientific way of thinking and the engineering way of thinking. And this is represented here in our diagram by sort of scientists, like the data scientists, business analysts, and the engineers, the data engineers, ML engineers, SRE, and app developers. The very first thing that you need to begin with is, what is the problem, right? And what are the, especially if we're following a rigorous type of approach, we want to check our assumptions. We want to establish certain metrics that we're trying to meet, rather than kind of tricking ourselves later on as we're building our models that we've created something really great, right? So create what it is that we're trying to, the success criteria that we're trying to hit basically in the beginning. And then we'll start to explore all of the data that we have available to kind of start to formulate the problem. Then we'll actually, especially if this is a team solving the problem, we'll want to federate the data so that we can access it from multiple locations. We'll want to clean it, and we spend a lot of time doing that, and we'll eventually label it, try to arrive at a sort of golden data set that we can use, especially for the validation process. Then we're finally at this portion in the process, which I think a lot of people focus on, right? Which is actually building the model. So going through a process where we look at the data, examine certain features of the data, and choose which to use, which are most promising to use to actually train a particular model. We want to also select a particular model, kind of test it, tune it, and eventually validate it and simulate it. And we might be doing the validation and simulation in many different types of environments, especially if we're doing something like building an autonomous vehicle model, right? It's not enough to just purely build the model. We'll need to build a whole system around it. We'll need to deploy it. We'll want to make sure that since this could impact human lives, we need to test it in multiple different ways, right? And then we'll deploy our AI system. And we're not done there because a good system will continuously monitor and validate that the system that's deployed is performing as we wish it to. This is sort of depicted as a sequential process, but just keep in mind that you're doing it right if you're revisiting prior stages of the process. And so it's kind of cyclical, circular, because you discover that, hey, there's some new information I hit in the production environment that I need to account for in my model. So I need to retrain my model, or I might need to select a completely different model, or I might need to collect more data, right? So you need to revisit this process as you go.
So there are a lot of lessons we can learn about machine learning systems and machine learning models if we look at the history of science, and I think it's more fun to start with the history of pseudoscience. So let's look at that. The first example of a pseudoscientific phenomenon from history is the idea of a trial by ordeal. And this is where we have someone accused of a crime and they're put in a dangerous situation with the assumption that if they're innocent, they'd benefit from divine intervention, and if they're guilty, they wouldn't. This was once a really common approach to criminal justice, but it was also way more effective than you might think. And an intriguing recent theory suggests that trial by ordeal was actually really effective because everyone involved believed that trial by ordeal was effective. So if you were accused of a crime and you were guilty, you absolutely were not going to allow yourself to be dipped in boiling water or whatever. You were just going to plead to a lesser punishment. If you were innocent, you would believe that you would be delivered by divine intervention, and so you would go through with the trial. And the person administering the trial knew that the only people who actually agreed to this were innocent. So it actually worked out. In our machine learning systems, we can often be right for the wrong reasons as well, whether that's testing an imbalanced classifier by only testing it on the common case, or other examples that we'll see later. A second kind of pseudoscientific phenomenon probably hits close to home for a lot of machine learning practitioners because it involves making predictions about the future. Successful horoscopes are often full of vague platitudes and rely on confirmation bias for the people who hear them. If you hear something that's vague and positive and turns out to be applicable, you'll remember that. If you hear something that's vague and positive and turns out not to be applicable, you'll say, oh, maybe we just haven't seen it yet. Similarly, a skilled fortune teller is often going to ask a lot of leading questions from their subject to gather information about the subject that they wouldn't otherwise have, which can make them appear to have information that they wouldn't have normally. This is really similar to the machine learning phenomenon of target leakage, where we accidentally train a model on information that it wouldn't have when we're making predictions. A third pseudoscientific activity we'll look at is the idea of dowsing for water. That's using a special rod or a forked twig that's supposed to vibrate when there's water underground. And this is another scientific challenge we see when we're building machine learning systems, the base rate fallacy, right? Many areas in which dowsing turned out to be popular had quite a lot of underground water. So maybe if you did a controlled experiment, you'd learn that using this forked twig is not actually better than just digging for water in a random place. Or you wouldn't have a controlled experiment to compare two different techniques for dowsing. We see superstitions in pseudoscience and machine learning as well. Right? How many times have you learned a new technique by looking at the documentation? Say we're looking at the scikit-learn classifier interface for XGBoost. And this has a ton of documentation, right? If I run help in a notebook, I'm going to get many pages of documentation, the first half of which are default parameters. Now, ideally, we'd understand what these parameters are and how they impact the model, but realistically, we don't do that, right? We sort of train the model anyway, just using those default values for the parameters. Now, this is bad for a couple of reasons, one of which is that a new version of the library might have different default values for the parameters. But we also haven't really done a controlled experiment to validate that this is doing the right thing. A more recent example that maybe some of you have run into is the idea of sort of prompt templates for dealing with LLMs. And if you think about people who've talked about how they've been successful using LLMs, they often have this library of magic phrases, right? And in 2024, saying, let's think step by step was like a cheat code to get a better answer out of an LLM. But today, the model is going to think step by step whether you ask it to or not. We use reasoning models today, and asking it to think step by step is just a waste of tokens. So another thing to think about as we sort of review the history of science and think about what does this have to do with machine learning is what kinds of explanation is science providing? And I want to contrast two different kinds of explanations. On the left-hand side, we have a teleological explanation. What is something doing? Is it doing the thing that it's supposed to be doing well or not? Now, we associate this kind of explanation with the natural philosophy of Aristotle and other sort of philosophers when philosophy was a much broader field than it is today. But this kind of teleological explanation is still useful in engineering and in medicine and in machine learning systems even today. On the other hand, we think of mechanistic explanations, which we tend to associate with the scientific revolution, exemplified by Newton here on the right. And the idea is we want to identify how something works and why it acts the way it does, rather than whether or not it's just doing the thing that it's supposed to do well. A lot of times, teleological explanations are essential as we're building machine learning systems. If I'm evaluating this system that I've just showed a screenshot of here, and don't look for these coffee shops, they don't exist. But if you want to evaluate this system, you don't have any way of knowing whether or not these are good coffee recommendations in general or for the particular user. But you do have a way to know how the user reacts to these recommendations. And you have a way to know whether or not the user keeps using the system. We might need to look at a model in the context of an overall system. By contrast, sometimes we need mechanistic explanations to figure out where things are going wrong. A great lesson from image classifiers is that sometimes the image classifier hones in on something that you wouldn't expect it to. For example, we have a classifier here that's distinguishing between running shoes and dress shoes, the running shoes on the top row, the dress shoes on the bottom row. But if we give it this example of someone wearing wingtips on a running track, it identifies it as a running shoe. Well, why did we do that? Well, if we look at what the model is actually responding to, we might see that the model is looking for the presence of a running track to identify something as a running shoe. So a lot of times we get these ML superstitions just by reusing advice or techniques that worked well in one context without thinking about why they worked. And the process of drilling down and identifying why these things work involves mechanistic explanations and engineering discipline. So I'll hand it back over to Michael.
Thanks, Will. Yeah, so the flip side of the scientific way of thinking is the engineering way of thinking in this. And we'll illustrate this through some of the examples of failures that have become kind of engineering lore, right? And for example, Ariane 5 Flight 501, this is a rocket that, took off in 1996, and 37 seconds later, it actually imploded. And the reason for this is that there was some, flight calculation software that was reused from the Ariane 4 that was repurposed for this new version of the rocket. And it was operating with data from sensors that were a lot more constrained than the new rocket actually had. And so when these more extreme values were encountered in the backup system, the hot spare, it had a sort of overflow reaction, and it failed. Shortly thereafter, the primary system actually encountered the same data, and it failed too. After it failed, it looked for the backup to see, well, could I hand it off to the backup? It couldn't, doesn't exist. So at that point, it uploaded debug output to the main flight computer. And the flight computer, unfortunately, looked at all of the debug and interpreted that as commands and self-imploded. So what can we learn from this? The software module that was used, that was old, actually was operating within its bounds. It was not incorrect, so to speak, right? But the overall system didn't take into account that there are more extreme values that needed to be upgraded within either the underlying component, or there needed to be a sort of system level change. Sort of similar example through the Mars Climate Orbiter, or MCO for short. This is a great example of where the thrusters system within the MCO, when it was making its way over to Mars, was expecting force measurements to be in pound feet per second, but actually it was in like Newton meters per second or something like that. So metric versus like imperial system conversion. And this actually resulted in computation that was way over bounds, and the MCO, as a result, overshot. We lost contact with it, right? So similar example, and I think these two examples illustrate an important point with interface contracts, right? With ML systems, it's not enough to have a model that is technically correct or certain software that's technically correct. We have to think about each aspect of the greater overall AI system that we're putting into play. So we have to consider as many of these operations are like matrix multiplications of different values, but we have to test our assumptions of, are we having sort of extreme values that we hadn't considered? Are they within range? And essentially for each component in an ML system, what is the contract that each component is adhering to? How does the system perform as a whole? Another great example of engineering failures is the Millennium Bridge. In the year 2000, London was celebrating a whole new bridge that had been very carefully engineered for vertical forces, but not for lateral ones. And the interesting thing that happened as a result was that when the bridge was opened to the public and people started to walk on the bridge began to sway laterally. And with this, it created a really interesting synchronization effect where people started to kind of have to march to the same beat as this lateral sway, which actually made the lateral sway worse. And there was this whole feedback loop, which resulted in the bridge catastrophically failing, right? So what does this remind us of? It kind of reminds me of feedback loops with algorithms that we have online, right? It's very common to get into sort of like a bubble where if you like certain things and you dislike other things, you might start to see more and more extreme versions of whatever your likes and were or your anti-dislikes were, right? And so we have an ethical responsibility from the engineering standpoint and a sort of just a practical one that, like, when we deploy a model or we deploy a system in production, we have to carefully consider and monitor that system in this production environment and make sure that just because the system worked well at one point in time, it doesn't mean that it will work well in the future. It doesn't mean that the interaction of users with this system won't actually evolve and kind of compound over time. Last example on engineering here. Knight Capital was a trading firm. They made automated trading software. And in 2012, they started to manually upgrade certain nodes with a new version of their trading software. They missed a couple of nodes, and the interesting thing that happened was that the old software was getting all of the same buy orders that the new software was, but it was trying to communicate with the rest of the new software to say, hey, do I still need to buy this particular stock? Or, and because it couldn't communicate, it just took it as a signal that it needed to buy more and more shares, right? And that resulted in another catastrophic failure where $440 million were lost at the end of this, right? So what's interesting about this is really having a good DevOps process, dev, staging, prod, having good CI/CD, having a way basically to roll out software systems, because an AI system is just another software system, and having version control, having a way to test everything. It's still extremely important in this day and age.
So now we'll look at a case study and we'll see how both the science and the engineering come together in a particular application area. I bet you've already interacted with a recommender system today, right? Any bets on how many you've interacted with? Just hold up fingers. At least one. So, if you've done social media, streaming media, search, if you've bought anything online, you've interacted with a recommender system, right? We're going to focus on retail here, and we're going to look at how there's sort of an elegant insight about this problem that turns into a model, and then how putting that into a system reveals some problems that we want to solve with a better model and a better system. So the basic insight is we might have tens or hundreds of millions of users and maybe millions of products, but we can meaningfully group users and products by similarity and find users with similar tastes or find products that are appreciated by similar users. So here we're encoding user product affinity as a matrix. In the row, you have a user's ratings. And in a column, you have all of the ratings that every user has made for a particular product. And most users don't review most things, so this is a sparse matrix. If a user clicks on a product, we can find all the similar products by finding the vectors that are similar to that product column. Now, to look at what's involved in solving this problem, let's look at a matrix that fits on a slide. This is a low-resolution image of Louis Daguerre, who invented the first photographic process. And this is a 160 by 125 element matrix, right? 20,000 values. If we wanted to find the column that was most similar to this, to a 160 element vector, sort of like finding the product similar to a product, we would have to do about 40,000 arithmetic operations. The complexity of this is on the order of the number of elements in the matrix. Now, the interesting thing is, if we have a lot of redundancy in this matrix, we can decompose it into lower rank factors that when we multiply them together, we get an approximate version of the matrix. That's cool because it saves us some space in storing the matrix, but the real advantage is that we can do that similarity search in this lower dimensional space as well. So we've saved about 3/4 of the space and about 3/4 of the compute if we're doing similarity search against this compressed representation. And if we can handle even more error, which we often can, we can save even more time. Now, I wouldn't be submitting either of these as my LinkedIn profile picture, but they're obviously still Louis Daguerre, right? And in recommender applications, directionally correct is often good enough. But we're also dealing with much larger matrices than these tiny ones that we can fit on a slide, and we're dealing with relatively smaller decompositions than these ones that we're looking at here. So instead of saving 75 or 90%, we're often saving 99.9 or more % of the time and space necessary. And we can use that to answer the question, hey, given that you bought this thing in blue, what are some other things that you might like, the things in orange? There's some problems with this model, though. And the first one is that we need explicit or implicit user feedback to make recommendations at all. And I mean, when was the last time you rated anything online? We might unfairly bias towards products that lots of people have rated, or give recommendations that aren't useful simply because products have similar profiles. Like, how many times have you bought a desk and then gotten an ad for another desk, right? Like, how many desks do you need? But I think the biggest problem is that this system really depends on having a lot of data. And you can't make predictions at all without a lot of data. And if you have a new product or a new user, you need to build in some extra sophistication into the system to handle those cases at all. So a better approach is sort of modeling user behavior as a sequence and using a transformer to say, given that a user has done these actions, looked at these products, put these things in their cart, what are they going to do next? And we can train a sequence learning model based on user sessions to predict the most likely next actions and what is going to be relevant to what the user has just done. What are they going to do next? That first part of this is predicting the next conditional probabilities for what the user is doing next. And this is an important part of making recommendations, but it's really only part of a recommender system. And so we're going to borrow some terminology from the NVIDIA Merlin team and say this first step is really just retrieving relevant things based on what a user has already done. The next step is filtering out the things that we don't want to show the user. I don't want a user to know that they can buy something that's out of stock, right? That's just going to frustrate them. I don't want a user to know that they can buy something that I can't ship to their country or their state. Given the things that we want to appear in the ultimate recommendation, we have another model that predicts how likely the user is to choose one of these actions. And finally, we have another rule-based system that orders these based on business criteria, say putting something with a high margin first, or if a user already has 5 items in their cart from one warehouse, we want to recommend something else that's in that warehouse and ship it all in one box. So we have the beginnings of a machine learning system here with this sort of aggregating user behavior, making a prediction based on the sequence of things that a user has already done. But in production, this whole pipeline becomes a subsystem made up of components. And all of these components are software. right? We version all of them independently, we develop all of them independently, but as we saw with the Ariane 5 rocket and the Knight Capital example, we really want to be deploying all of these things in lockstep. So if I upgrade a bunch of components to version 2 and something is still on version 1, my system is probably going to misbehave. So really, we need a way to manage the versioning of these systems, and we need a way to make sure that our deployments are automated and disciplined and happen all at once or not at all. A second thing we need to do is we need to track how well individual versions of the system are running. So if we know what components we're running and we know how well the system is working, we can say, hey, given these constraints, how well are we doing versus how well we were doing a month ago with a different model? We're going to maintain 2 separate training pipelines for the 2 models that we're using in this recommender system, and we're going to need historical data made available at scale to do that. But we're probably not training the model on raw historical data. We're probably transforming it and tokenizing it somehow, and we may take different approaches over time. So just being able to say this is the current version of our historical data isn't as useful as being able to say we can go back to the previous pipeline that we used to train a previous version of the model. This is really essential if we want to do controlled experiments over time and see how the model has improved or not over time. So being able to roll back to that previous version. Another concern is we want to support data scientists. We want to support the people who are working on this modeling approach. And this means that we need to give them compute on demand with a controlled environment so that they can reproduce their work and share it and collaborate with their colleagues. We need to make it easy for them to track their work with version control. And, often we're standing on the shoulders of giants when we're doing data science. We want to make it possible to understand and audit the open source libraries that they're using in this work. Finally, we want to take all of these details about what went into training a model, the version of the code, the version of the data, the version of the dependency libraries, and any hyperparameters we used in training the model, and we want to store these in a database along with the sort of results of that model from validation. So we can do a controlled experiment and say which of these things work better for our problem in isolation, and then track these things in the real system. We're going to collect feedback from the real system, which enables us to have more training data for our model in the future, and also see how things are going. And we're starting to get a picture of a complicated system here. We have a lot of software components working together. Every one of these arrows is doing some heavy lifting, and it's some place where something can go wrong. And we really want a way to make sure that this stays up and running without a lot of human intervention. And we want to get alerted when things go wrong, right? So this is really a simple picture, but you're starting to get a picture of all the kinds of things that can go wrong in a machine learning system. So I'm going to hand it back over to Michael, who's going to talk about how to see the space that makes this manageable.
Yeah, so let's revisit MLOps and our definition of MLOps. You'll recognize the process and the people, right? But what are the components that should be involved here? And how do they enable the scientific part of the process and the engineering part of the process? Which you might recognize is, the top components are infrastructure agnostic, following a scientific method, and interestingly, the bottom part are infrastructure aware, because they're targeted towards the engineering aspect of the process. So starting with one component, especially if we're thinking about like teams working together and having tools at their disposal, a very important part of the process that is a lot of time is spent is around data wrangling, analytics, labeling. So having tools that actually facilitate that are super useful to the MLOps, to the ML development process. For labeling, for example, you could think of tools where there are human auditors that are actually labeling the data, right? So critical piece here. Interactive development, Will talked about it, very important for, as you explore the scientific approach and the scientific method to kind of test out hypotheses. And sort of the standard today is like having a Jupyter notebook with a resource that you can, tinker with the data, tinker with the model, and interactively kind of develop. Will also talked about experiment management, super critical. You could think about this as sort of, in this era of ML and AI, like the version control system at the heart of how do you try different experiments out, but how do you track also all the permutations of different things that you're doing and arriving at a sort of audit log of like, what experiments worked versus which kind of experiments didn't, and also the data that you're using in the process and the software components. AutoML is just really an extension of that. If you think of like algorithms that run many different permutations and follow a certain algorithm, it's just experiment management plus an algorithm. Then the bottom here, we have data management, critical to pretty much every aspect of the ML development lifecycle, right? And you also want version control here, right? If you're storing data, the data will change. You label it, labeling might have issues with it. There might be additional versions of different labels for the same data even. And you want to keep track of all of that. And if you're not tracking the data, you're also not tracking the versions of things, right? Feature management and pipeline management. As you engineer different features, you want to serve them and use them as part of the training lifecycle. So useful to have software and tools that facilitate that. And pipeline management, you could think of running different tasks or different aspects of this process in a sort of automated fashion. So being able to say, take certain features, train a model, deploy that model or wrap that model up in an overall software system and then deploy it in an automated fashion. That's all pipeline management. Then model ops, really you could think of this as model serving and monitoring the model in production. Especially with Gen AI, this is a very popular area because you can just pick models off the shelf and kind of fine-tune them and deploy them in a very quick fashion, but it's still very important to monitor and see how they're performing. And then finally, sort of the unsung hero in a lot of MLOps is infrastructure management and scheduling. Certainly it's of huge importance at NVIDIA because you want to make sure that you're tapping into the resources in the most efficient way at your disposal. Are you using GPUs effectively? Are you using other hardware effectively? How are you scheduling all of the workloads, especially if it's a large team and lots of resources or it's a huge scaling problem? This becomes more and more important. So all of those kind of components are really generalized, and we have recommendations for each, which we've given in previous years, but it can get a little bit overwhelming. I think if you're just trying to get started, just know that there's a lot of end-to-end ML platforms that use a lot of these components. So if you go to the CSPs, you have AWS SageMaker, Google Vertex AI, Microsoft Azure ML, all of them offer pretty decent solutions to get started with. If you're looking to level up, you can kind of look within the space for just experiment management, model ops, and infrastructure management and scheduling, and you can build a more sophisticated system, I would say. Now I'll turn it over to Will, who's going to try and convince you that essentially in this new era of LLMs and generative AI, it's the same kind of depiction.
Yeah, so for those of you who are thinking it's 2026, why are you talking about classical ML? This is your part of the talk, right? So there are a lot of similarities, though, between generative AI systems and classical ML systems. One important difference, though, is that you're usually not training your own foundation model. I mean, if you are, talk to us. We want to hear about what you're doing. But a lot of these parts of the process are still really important, though, especially like having good evaluations for your problem, right? Are you actually solving what you want to solve? We'll see an analogy, though, with classical ML systems in this example of LLMs, right? LLMs are really impressive off the shelf, but a model by itself is not sufficient to solve a problem, right? An LLM might seem a lot more powerful and interesting than the low-rank matrix search we were doing, but by itself, it can only answer questions that it's been tuned to answer with data from its knowledge cutoff. So I can get a limerick about jackdaws. I cannot get a limerick about jackdaws with something that happened today or something that's in my private data. So we need a way to solve this problem to put this model in a system. And we need a way to identify documents that are similar to a user's query, rank them and filter them, and then combine them with the user's query and to make an answer, right? A useful answer. And if this sounds familiar, it's because we talked about a very similar system that does very similar things earlier in the session. So retrieval augmented generation is a pattern for augmenting LLMs with relevant context. And it turns out to be a complicated machine learning system as well, where we issue a query that depends on having these embeddings that we can search for documents. And the query causes a number of interactions between the different models we have and the LLM. And finally, we want to have guardrails to make sure that the query is appropriate, that we're not asking a support chatbot for help with our homework, and that the responses are grounded in truth and appropriate as well. So there are really a lot of similarities here, but we also see sort of important subtle differences with LLM systems and generative AI systems. And we see that a lot of these similar places have additional responsibilities and additional things that we care about. In these cases, a lot of problems become bigger. So there are a few things we want you to come away from this with. And the first one is that system concerns matter whether you're solving big problems or small problems. Right? We saw that retrieval augmented generation, which is a pretty sophisticated thing for most enterprises to be doing in 2026, has a lot of concerns. But even if you're training a linear regression model to predict the cost of real estate based on area, something anyone can do with high school algebra and a pencil and paper, you need to think about whether or not the model is applicable outside of its training set, right? You don't want to sell an apartment for negative dollars per month. System concerns also matter at every scale of deployment. If we have 10,000 nodes, and each of them might fail on average once every 10,000 hours, we're going to see a failure every hour. How do you deal with that failure? How quickly can you recover from that failure? We saw in the Knight Capital example that if you have 8 servers and one of them isn't running the right version of software, you're going to have a really tricky failure. Can we handle that case as well in a more automated way? But even on a small scale, you may be running a lot of machine learning environments on your local computer to allow an agent to interact with your code. Have you given the agent access to the right things and not given them access to the wrong things? It's a great question. So we started by looking at how a lot of people have idiosyncratic views of MLOps and are only focusing on part of the problem. We really wanted to sort of give a broader view. And we saw that we can benefit from science and engineering examples throughout history, whether those are looking for water in fields in Western Europe in the 18th century or looking for water in the atmosphere of Mars. We saw science and engineering come together, how models turn into machine learning systems, and we looked at a taxonomy of how to make sense of this space and build a platform that works for your organization. We don't have time for questions right now. We'll take some in the hallway track, but we have some great opportunities for you to learn more. Immediately after this session, there is an MLOps 201, and tomorrow afternoon there's an MLOps 202. If you go to all 3 of these sessions, you'll be really well equipped to continue on your MLOps journey. We also have a special opportunity for questions at 4 p.m. on Wednesday, where we have a Connect with Experts session. Michael and I will be there along with a bunch of other NVIDIAns to talk with you about your challenges and ideas in this space. And this has been a really rewarding experience for us when we've done it in the past. It's been great to spend some time with you this afternoon. Have a great rest of your GTC.